Like in the lung, the fascinating details lie in the mechanisms of the mixing across that mixed regime region. We're still working through the details, but we think there are two principal mechanisms that might interest you. Both involve taming the messy AC transients that exist in turbulent winds. The first involves the mound's impedance. The mound acts like a low-pass filter for the broad-spectrum energy in turbulent wind. At the surface, where the mound first encounters the wind energy is broad-spectrum, comprising transients that span a wide range of frequencies. If you follow flows within the mound, this spectrum is filtered by the mound's network of tunnels. We think the complex interweaving of the reticulum has something to do with this. In the surface conduits, the spectrum is still quite broad, with the upper frequencies being damped somewhat. Deep within the mound, nearly all these high-frequency components are damped out, leaving only the low frequencies to drive flows there. Within the nest, of course, these transients are damped out completely, leaving only the DC gradients in oxygen and CO2 concentrations, just like in the lung. Now we can see one of the mechanisms for promoting mixing. Remember that the air spaces of the nest are connected to the mound through the chimney in the center and peripherally through the underground extensions of the surface conduits that envelop the nest. Thus, the nest's peripheral air spaces will be driven by high-frequency transients, while the center spaces will be perturbed by low-frequency transients. This differential driving will perturb the interface between the two air masses. Occasionally, there will be sufficient disturbance to promote a burst of microcirculation between the two. This is why we see air coming out of the nest into the mound as bursts or puffs of air. Another possible mechanism involves a resonance phenomenon. The tunnels in the mound are long enough to form resonant structures, something akin to an organ pipe. One can calculate these expected resonance frequencies. The surface conduits, for example, can be as long as 3 meters from top to bottom. Air in a pipe this length will resonate at about 20 to 25 hertz, just below the audible range. We know, in fact, that the mound has a resonant frequency. We employed a sound engineer, John Crowley, to come to our site in Namibia to measure this. To do so, he put a speaker on the top of the mound and found that the mound resonates strongly when the speaker is driven at a frequency of 20 to 30 hertz. This suggests another form of mixing, called variously acoustic mixing or Rayleigh mixing. If the column of air contains a stratified mixture of gases, driving the column at its resonance frequency will promote vigorous mixing across the boundary. You can see this here in this video. This is a plastic bottle with a stratified layer of smoke. We've illuminated it with a sheet of laser light from a laser level. The bottle itself is on one end of a long pipe, and on the other end is the baffle of a speaker. We're driving the speaker at 3 different frequencies, 4 Hz, 8 Hz, and 16 Hz. When we switch on the sound, look at the vigorous mixing that is driven by 8 Hz, but not so much at the frequencies bracketing it. This is occurring with no bulk flow of air. This is acoustic mixing at work. We think something like this might be happening in the surface conduits. Within the surface conduits, there should be a stratification of air between the subterranean parts, which communicate with the nest's peripheral air spaces, and those parts in the mound that communicate with the turbulent atmosphere. If the broad-spectrum turbulent energy that we see in the surface conduits can be tuned to resonate in the surface conduits, as we strongly suspect, this could promote mixing of air between the upper and lower parts of the surface conduits, and this will promote gas exchange.